Assalamu alaikum warahmatullah. So today we will talk about gradient descent in practice. So we will plot common functions and we will see how gradient descent minimize and how it works actually in practice in Python. So let's get started. I will switch to my screen. Okay. So it's terminal. I'm in Mac OS operation system. So first of all, let's run Jupyter Notebook. Jupyter Notebook is local version of Google Colab. We may say like that. And I prefer this one, and I will tell you how to do in here. It's better. So okay. So desktop, new Python kernel. I have this kernel. Okay, entitled. So let's rename it. So please feel comfortable. So it might take a bit long time, but it is practical. So we will do it together. So what we are doing now is that gradient descent in practice. I think I should make it bigger. I think it's much more clear right now. See, I see. Okay. So we talked last time about gradient descent. So let me to recap about it. So we talked about gradient descent. We say that gradient descent is that it is optimization function which is iterative and it uses a derivative. So and it has a learning rate so that previous x point minus learning rate multiplied to the derivative of that function. By doing that, we are finding the next point, next x. And in next term, if we repeat this thing many times, and each step of repeating this thing, so this is one process, second process, so this process is called as epochs. We call it as epochs. And we talk that there are first order derivatives, partial derivative, second order partial derivative. So for today we will talk about how gradient descent will work for this function, very simple function, because we know that the derivative of this function is 2x from last session. So we will talk about this thing and we will plot this function. And the second thing is very famous function. The function name is Himmelblaus function. So it's very famous function, and we will, as second practice, we will use this function to find gradient descent and how the gradient descent works in this function. So let's start. Okay, now I think it's clear, right? So we will do for two functions. For the first function, we need make sure that we have numpy. Import numpy as np. We have numpy, no problem. And for plotting, we may use matplotlib. Matplotlib is like very good, but you know, I need more flexibility, and the second function, Himmelblaus function, requires like if we can interact with that graph, with that plot, it is much better and makes much better sense. So I will use this plot line. Yeah, plot line. So I am importing plotline dot graph objects as go. Okay, I think I have, yeah. I have a plotline. If you don't have, you will use pip install plotly like that. So we have imported these libraries, right? So first of all, first function. So we can use a markdown, and we will say gradient descent in fx equal to x of square. Okay. So for that function, let's define that our function, this function, requires x, and it returns what? X squared. So this is how we write the x square in Python. Actually, I think, yeah, now it's clear. So now the derivative of this function of x equal to what? So we said the derivative of this function, will be that the square will go down, so it will be 2x. 2 multiplied x. We can write like this, but it is, not good, like not beautiful, not elegant. Okay, we have x, we have dfx, and now let's create the starting point. So x initial, let's define it as 10, and then learning rate, let's make it 0.01. Note, later we will play with this rate. It is important number. Yeah, learning rate and epochs. For now, how many epochs we want to do? We want to do around, let's say 50, maybe. I don't know. Like we will play with that also. So we can play with epochs. We can play with learning rate. We can define starting points like based on our need. So we can say like here also note modify later. It's better to use this kind of note notation, note mark. It's good. Or we can use, like xxx, change to see how gradient works in different scenarios. Okay, we have epochs, we have learning rate, and now what we say is that for epoch, in epochs, okay, so like it will give error, it will say bad thing. So for epoch, what we want to do for epoch, I think it's like, okay, let's do it like for what? For epoch, for each process, for each this process, for epoch, in epochs, what we want to, for each epoch, we want to find new x value, right? New output. So new output is equal to what? We said it should be last output, last x, minus learning rate multiplied to what? To the gradient, to the derivative of the function. So I will call this derivative df, and I will give the last x. Okay, so that was logic, right? So this one. So again, I think you are sleeping. So this one is this one, okay? New x equal to last x minus learning rate multiplied to derivative of fx function. So in our case, it is this function, derivative of the function. So it's that thing. we are giving last x. Yeah, for now I didn't define last x, but like in theory, in how we understood the gradient descent is that we are finding this thing and I'm finding new x, and the last new x is the latest point, right? So now we are finding x. Okay, so last x, we need to define last x. If we define this last x, we will process this new x, right? So last x, what is last x? In order to find last x, that last x means that we will do each time this epoch process, and we should take the latest point. So each time we will do this epoch process. For each process, for each epoch, we will do process, and for that process, we need to get the latest point. It is similar to data type of list in Python. So, for example, if we give the list, for example, my list, if I give list and I will give x, if I give like value 1, 2, and I will, if I will call my list -1, it will always give the latest number, last number, last. So the logic's similar, right? So we can implement that into this Python by using this list. It means last x is my list -1. We are getting the latest point in -1, and it is last x, so that it will be x. And if we will say my list dot append new x, so now we solved almost. Look, so we are getting the latest point in our list, and we are calculating the new x. We are putting new x into our list, this list, and if we will call next time -1, it will give us this new x. Make sense? Okay. Again, I am repeating again. So for each process, there is one list, assume, and I am getting the latest point into that list, and it is last x point. And I will use this last x point, and I will minus learning rate, and I will find the derivative of that function with respect to this number, and I will get new x, and I will put this new x to the list, so that next time, for the next process, I will take this last x as a new x of previous process. So I think you got it, right? So here everything is good except this my list. What is my list? Like, the naming is bad here, right? So we will say this as gradient descent path. And the first point, as I said, it is x start. Okay, I think x start is not good name. Initial x. Okay, initial x. Oops. Initial x. And I don't like this name. Initial x. Okay, we put this one, and if you put gradient descent instead of here, it will make sense. Gradient descent path -1, and we will find the derivative of that thing, and I will append to that gradient descent path. And after each process, I want to print next x is new x. So let's run this thing. Okay, we are having error. Int object is not iterable. That's true because I don't want 50. I want range from 0 to 50, right? So I will say range. When I use a range, it will go from 0 to 49 actually. So let's try again. So now, so we give the point x10, it will go to 9.8, 9.6, 9.8, something 7, 6, 5, 4, 3, 2. It's like it's learning, and it is, we are processing the gradient descent with learning rate. So, and we have this gradient descent pass, and this is as a list. So instead of the next one, I will, so I will just print the gradient descent. I think I don't have autocomplete here. So now we are having the gradient descent pass. So this is pass of our gradient descent. So of these epochs. So first it was 10, and it become 9.8, 9.6, 9.4, and it goes to 3. If I change this to 100, it will be what? Maybe it will go to 1, yeah, it's 1.32 something. So that's numerical representation, right? It doesn't make sense too much, right? So now we have this result, right? We have function, we have gradient descent, we have derivative of that function, we have the path of our gradient. So I can draw a plot. I will plot that x square, it's parabola. I will then put this path, this gradient descent elements into each point into that graph, and you can see how it is minimizing the function. So okay, so I will clean it up. So gradient descent path, now it is as Python list. So I will convert it to the NumPy list. Gradient descent path. Gradient descent path as np equal to np array of gradient descent path. Okay, we have the gradient descent path as NumPy. So what we need, so first of all, we should figure out the in the plotly documentation. If you check plotly documentation, first we should define this fig equal to goal dot figure, and if we do this figure, and we will give, first we will give nothing. I think that's okay. Yeah, and I will give fig dot add trace. I'm adding the parabola trace. It is go dot scatter x points. So x point is so for x point we should give here range. It should be so it should be a whole plot, right, from certain point to certain point. So we should create now random values for the x. So I will call it x range, maybe x range. I hope it makes sense. And I will put y. It will be that I will use f function, and I will give the x range. And mode, I will define the mode is equal to lines. Yeah, lines. I can see. Okay, lines. and I will give the name. So it is f function equal to x square. So I don't have x range here, so I will create if x range. X range is just random numbers. So in NumPy, to create that random numbers from certain range, we will use NumPy len space, and I will give -11 maybe to 11, and I will give how many points I want. Let's give 100. So I have x, I have y, and if I plot it, can I see it? Okay, I can't see it, but I can say fig.show, and I can see it. Oh, I can't see it. Why? Anyway, we will figure out, because maybe I should add fig.update. Fig.update. Update layout. Title equal to interactive plot of the or simple function. I give title. What else we should give? To make everything clear, I will add x-axis title equal to x. Yeah, small things, but y-axis title is what? Of course, y. And then outer size false. We don't need it. Width equal to 800. Height equal to 600. If I plot it, okay, here's something wrong with my Jupyter notebook. It should work, but it is not working. Maybe I guess maybe I should update my plotline. Let's debug it. So it happens. Pip install plotline. The requirement already satisfied. We have plotline. Okay, we have problems, so I will search the internet. Why the plotline is not showing in Jupyter? So it's common problem. So Stack Overflow is good place to check the problems. Okay, so for hours, okay, it doesn't work in notebook. Okay, this problem. So I will give upvote, like upvote, and let's read the answer. So this answer, you need to change init node move to remote connected equal to true if want to work in offline mode. Jupyter Lab extension. We can install this one, or we can use the GoY iPlot instead of Go. Plotly offline. GoY init notebook mode. So let's take this thing. So they are saying that if I put it here, offline mode, and I will set this thing. For professionalism, I will take this thing, put source. Source important, we should put source. And let's run it again. And here we should not say fig show, it was POI iPlot. iPlot data trace 0 trace file basic line. Okay, basic line. Okay, we have figure, a trace. Can I plot this figure if I give this figure? Oh, here's problem data. File data equal to trace IO figure trace. What if I use? It means it's saying that I need to use only this one. Let's redefine. So I should stop it. Stop it. I should rerun it. And now I can see the plot. Okay, now it is working. So this plot. This is our function, fx. Okay, there's a small bug. It's okay. And how can I put this layout? It's not, you know, like it's not good. It's not professional here. In case you want Jupyter Lab, you want to install Jupyter. Here's that problem. And trace go, trace 0, trace 1, I plot. I think the guys are they are not reading the documentation. Let's read documentation. Really? P-O P-Y-O P-Y-O. Show link, validate, export to plotlight image, file name, tweets, okay, autoplay, animation outputs. Okay, now we have I plot figure or data. It means I can give the figure. I can give easily this figure, you know, figure instead of data. If I give figure, show link, let's make show link true. Show link equal true. True. Link validate true, image equal to none, file name. Do I need to give file name? Config autoplay true. I think I don't need to give this file name also. Okay, now we figure out. See? I can give the figure. Interactive plot of simple function. I can write, like, you know, here I can write some kind of command. I can't write command yet. So it's like later. It's not our today's topic. So yeah, I plot this function. I plot it, the function, but I haven't plot our step of going from certain point to the minimum point of the function. So I have the list, right? I will plot this list into this graph. That's all. So just to make it clear, I will delete this data, update layout. Here I will add figure.addTrace. I will say will be go scatter. And for x, I will give what? We will give the gradient descent as numpy, and as y I will use the derivative of the function, and I will give gradient descent as I think using numpy or not using numpy here, it doesn't make big sense, big change. So it's like I will like, let's see for now what will happen. If it's not working good, I will switch back. Markers, lines. So here will be also line from each point to each point, and there will be also scatters points. Mode, I defined mode, and I will give name. Name is equal to gradient descent pass. As a pass, let's replot it. We are having error. What kind of error we are having? Infinite view string mode property of scatter marker plus line markers. It should be markers. At trace got unexpected name. Okay. Really? There is no name. I see here it should be, like I make small mistake. Yeah, x gradient descent equals scatter, and one more. We have gradient descent is from 10. No, I think no. Here I shouldn't give I should defix. I should only give the original function. So here now we can see the steps. So here are our steps, So we started with this 10 of x. X is 10, and we are going step, and our like epochs, we use epoch of 100, right? And it goes to here, but actually the minimum is here. So gradient descent is first order derivative optimization algorithm is using for minimizing a function. So actually it's minimizing, yeah. Now like we are going from certain point to certain point, so minimizing. So let's change the point from 10 maybe to 7. Let's try again. Initial point, I will say 7. Let's do it. This one, I don't need this one. I will just cut it. I will draw it one. This one, okay. Now we start from 7. It's going to, okay, it comes up to this point, 0.9. So you can see this happening. So our learning rate is sufficient, good. But if I increase the learning rate, our gradient descent will perform bad. For example, if I give 1, it will be crazy. So actually, it improved right now. So if I give 0.1, it goes from this point to this point, and it reaches to the 0. It reaches to 0. But if I give very huge number, it will, it will become chaotic, stochastic somehow. So it may go to this side, to this side, to this side, to this side. If I give, for example, 0.5 maybe. So I think if I give 0.5, it goes directly to 0. Something like that, The gradient learning rate is important. So, epochs are important. So let's define it 10. Let's define learning rate is 0.9 maybe. So now we can see the actual problem here, that it goes from here to here to there to there to there. So now it is not learning, it is going somewhere around, and that is not what we want, because it is very long. So it's better if we go from this line and make small steps and go here. So finding the learning rate is also, or defining learning rate is also important. So here you can see it clearly. Okay, that's about first function. Pretty clear, right? So you learned about these things, and you also learned how to use plotly in Jupyter notebooks. Okay, now we have gradient descent of this function, and now very cool thing. So that this is very simple function. There are many different functions, and it is ideal world, right? It's just the parabola. It's like going this function, but there are many tons of different functions. There are many beautiful functions, 3D functions, some kind of beautiful graphs. So now we will use Himmelblaus function, and we will find the gradient descent of that function. Yeah. So let's hurry up. Mark down. So Himmelblaus function. Gradient descent. It's better, you know, like if I cut it, put here. Himmelblaus function. For people who don't know that function, I will show you a graph. This is Himmelblaus function. So now we will plot this on plotly, and I will put, for example, initial point from here, how it will go. So here we can see this is minimum, this is minimum, this is minimum, saddle point, minimum. So as I told you, gradient descent main usage, main aim is to find the minimum of a function, and we will see visually how our gradient descent is actually performing, actually whether it finds or not that local minimum or local minimum, yeah, or global minimum. So I think you understood that Himmelblaus function. Now again, what we will do is that we should define the Himmelblaus function, the Himmelblaus function. Sorry for that. You can see it was 3D graph, right? We have two input, and as a result, we need to give, you know, we need to give numpy array or just value float. So it is what it was at x square plus y minus 11 square plus x plus y square minus 7 and square. Himmelblaus function. I am rechecking again if there is typo or not. I think we are good to go. That's Himmelblaus function. And next thing is that we should find derivative of that function. So I say Himmelblaus gradient, we receive this x. So now we will find partial derivative with respect to x value, and we will find partial derivative with respect to y value, and we will give these values. So the derivative of df with respect to dfx is equal to 2 multiplied by x square plus y minus 11 multiplied times 2 times x plus 2 times x plus y square minus 7. So that is derivative of dfx with respect to of the function with respect to dfx. We found dfx, but next we should find dfy. dfy will be 2 multiplied by x square plus y minus 11. Same, it remains same, but it will be plus 2 square x plus y square minus 7 multiplied 2 multiplied y. So that's derivative of the Himmelblaus function. It is a bit complicated to find this derivative, but our today's point focus is not to find the derivatives of these functions. Our main topic to understand how gradient descent works. So if you like learn a little bit about derivatives, you will figure out how this is calculated. So we find these things and we should return this thing. I will say np array and I will give this dfx df dy. Simple enough. So we define the function, right? It's the same process. So learning rate. Zero 0.01. Like usually 0.01 is good starting point, and 42 is very good number also. Learning rate, initial point. For now, let's put initial point minus 0.0, minus 1, minus 1. And we should define epochs. 100. Maybe we can use 1000 also. And what we said, for epoch, in range epochs, yeah, now we feel a little bit confidence because we did for the small function, and now we are doing for complex function. For epoch, what we need? Last point, and we will say new point equal to what? Last point minus learning rate multiplied to what? Multiplied to gradient descent, to grad. So grad is Himmelblaus gradient receive what? It receives the last point. And I think that's all. And what was the point is that we have path, right? Gradient descent path append new point. And we said last point is equal to gradient descent path minus 1. So gradient descent as equal to empty array, and for the empty array as initial point we are giving dot append initial point. I think this makes like more readable, right? This is more readable. than just putting this initial point into here. Write in comments if like, do you agree also or not? Epochs, we are having last point, we have gradient descent pass -1, the latest point, Himmelblatt's gradient. So it receives 2 points, but we are giving 1 point. But last point is that it is this one and this one, right? Last point. So now if I run, it will give me error, print new point. So if we have some kind of problem, it is okay. Now I have problem, type error, it is okay. Missing one value, why? Will it work? I think it didn't work. New point, new point, new point. Gradient. I will just print new point. Okay, there is error. What kind of error? Is that last point is numpy array. So last point 0 will be x. Last point 1. So you see, initial point, this one, it is numpy array. Just list, we can call it list. And we are giving 0, it means first value, first element, that is x. X, this one is for y. It's just for I define it. You can change it. But usually we define it like that. We giving this 0 as x and this one as y. And we are receiving this new point. And then that's all. And we will print. Let's see it. For epoch, in epochs, okay, there is another thing. I didn't make it well, you know. Epochs. Now let's try. We are having that. And let's prove it, like whether my last use like this syntax is valid or not. I'm not sure. Let's check it. Last point. This syntax is good, you know. Instead of writing like this, we can write like this. It will just like open the array, just give the elements. So we're having these new points. That's good. We are saving new point to the gradient path. Now it's good to save gradient descent. Why it is in red now? S and P. So yeah, interesting. Gradient descent S. We save it as this thing. So now we have gradient descent, and now what we want to plot it, right? We want to see how in that mysterious function or in mysterious environment, it's learning from certain point to certain point, how it reaches. So let's test it. So for that, we will use plotly also. And we said that to save some time, I will just copy it. I think I need just to copy this thing. Just let's copy this much. We should give x range and we should give y range. So we will give from -11. Okay. P lean space -11 to 11, 100. We have x range, we have y range, and I think that's enough. And here I notice that we should also give something like this: np.mesh grid, and we should pass this x range, y range. Let's call it x range and y range. Let's delete this one because we don't need it for now. Interactive product of what? Of Himmelblaus function. So we have x, y, and we need z. What is that? That's obvious. Himmelblaus function, and we are giving the x range and y range. So now we are not giving only one value, we are giving the array of numbers to this function, and we are receiving z as a numpy arrays. It's very handy. So before doing that, we should put it here after meshing. So if you don't know about mesh grid, I also don't know very well, and I want to read documentation, we will use np.meshgrid. Makes NZ coordinate array for vectorized evaluation of NZ array scalar vector field over NZ array grid given one-dimensional coordinate. Okay. We give one the array and we receive list of NZ arrays. Yeah. Makes vectorized form. So we have Z, we have Y, we have X. Now we can plot. Go figure. Inside figure we will use data. We will give data as go dot surface. It's how we will create the 3D, X equal Z equal to Z range, X equal to X range, Y equal to Y range. Okay, and I think clear, and color scale equal to, we reduce and opacity 0.8. If we comment this and if we plot it, we can see our function, oh my god, this is our function. But like I think from 10 to 10 it is like very big. I mean, like if you put from minus 5 to 5, they should be the same, otherwise we will receive error. Now if we give 5 to 5, we can see clearly, like here is minimum, here is minimum, like we have here minimum, there minimum, 1 2 3 4 5, but the optimum, the global minimum, I think this one. So our gradient should go here. So actually our gradient did its job, so we just need to plot it because we saved the gradient descent path into this array. So we will now add this trace. We will say fig dot add trace, go scatter 3D, so it's like documentation, and then we will give as x what we said x. It is gradient descent path as np, and we are giving everything but 0. We will give y is gradient descent as numpy everything but at index 1, and we will give z equal to what? It is Himmelblaus function, which receives gradient descent as np, and we will use our secret notation. Actually, it's not secret, but not common, you know. This one, we give z1. I think we have z1, and we should give mode that markers plus lines, and we should give marker size. Okay, marker dict size equal to 5, and the line dict, it means dictionary, size equal to 5. And actually, I think for this one we shouldn't give that. It's saying we should give color equal to red. We have line, and now we have to give name. Name is what? Name is Himmelblaus function. We have one. We should close it. We should close again. Himmelblaus function takes two positional arguments, but 101 were given. I think, yeah. Here, this notation doesn't work. So we should give, like, we should say all and 0. And we should say gradient descent as np all at position 1. So let's run it. Now it's like done. So now we can see our pass. So I started at -1 location, -1 location, and our z, the resulting z, is 170. You can see it, right? So I will zoom it in again. So our function goes from here and it goes to the here. It's almost reaching, almost. So let's say function minimum coordinate. Here, like, we have actually the position of their minimum. One local maximum and 4 identical local minimum. Okay, we have local minimum at that point, like that they are all identical, same. So okay, I will just put it here. So now it is reaching from here the minimum almost. So now we can play around. So now we can see that actually the gradient descent is working, and we are giving certain steps and it's going to certain place. If we say that if we increase the learning rate to something like 1 or 9, so let's give 9. So let's see what will happen. Okay, we are having overflow problem. Overflow, we discussed overflow last time. If you check last video, we will talk about overflow and underflow. We having here an overflow problem, and if we plot it, then it's saying we can't plot it because there is no representation. They don't represent. Overflow means special thing. It means just infinite. It means like that we cannot represent it as it is. If we give the learning point 1, still overflow 0.001. Okay, we have a learning rate. I don't need this one. I give very small learning rate. So that it is not moving actually, you know. It is going from one place to another place, but making very, very small movement, very, very small steps. If I put it 1, okay, we are having a problem, right? 0.9 and 0.3. And if we plot it, here it becomes, we can see here now it's crazy, you know. It goes from one point to minimum, and it goes back, it goes to another place, and it goes like, it makes certain expeditions, goes from one place to another place. Like, it's not learning, it's not what we want. So a learning rate is that much important. So you can play also around with another value, is that we give this one, right? Initial point. Initial point is also important. Here you will understand this pure uh, basement of gradient descent and how it is like working, and it is fun. So that's enough for today, guys. I hope you enjoyed this session. It is almost 1 hour. And yeah, thank you very much, guys. If you like this video, please thumb up, share with friends, and write this thing by yourself also. If you understand, write in comments that it helped you, or if you have questions, write in comments. I'm trying my best to like explain these things, and I'm very glad that you are on the same track with me, that going with this kind of base things, and from small steps toward to the transformers architecture, or towards the modern architectures. So thank you very much, guys. See you next time. Bye bye.